Welcome back to ECE 442-542. This is the last lecture, and I need to correct the typo that is in this particular lecture. This is component D in lecture 6.1, PID beginnings, P being the proportional. We want to know, okay, can we learn a little bit more? And this particular lecture is sort of teasing us into what we might be able to expect from sketching a root locus diagram. So let's look now at this system. This is example 2, and say what can we achieve using proportional control. We now have g of z is equal to 1 over z minus 3 fourths. Z minus 3 halves. We want a proportional controller k. Is there a stabilizing value for k? Can we find some gain k that will stabilize that system? I hope you can see that in fact this system has one of its open loop poles at 3 halves, the other one is at 0, but all it takes is one bad apple to spoil the whole bushel or the whole collection. And here we have 2 apples or 2 poles in our open loop transfer function. That particular pole at 3 halves is outside the unit circle. The magnitude of that z is 1.5. We're starting with an unstable system. Can we stabilize the system for a value of k, or is there actually a range of k that would allow us to stabilize the system? Let's look at the closed loop stability. Again, here's our unity output feedback, negative output feedback configuration. We have the controller, which is a constant gain controller. Here's our plant, and we're using a specific plant, 1 over z times z minus 3 halves. The plant now is second order. We can derive, using block diagram algebra, the closed loop transfer function. That's kg over 1 plus kg. For a specific controller, a proportional controller, we want to now ask or address the range of k for all roots of 1 plus kg of z to equal 0 to lie inside the unit circle. We want to know, are there values of k that exist that allow the roots to simultaneously, of this characteristic equation, can we simultaneously get all of those roots to have magnitude less than 1, or to be inside the unit circle? And if that's the case, then those values of k would produce a stable closed loop system. And that's actually what is investigated when we draw or sketch these root locus diagrams of a system g of z. We are interested in the closed loop behavior, which is governed by the denominator expression 1 plus kg of z. We set that equal to 0, and that now says that k, g of z, if we simply add minus 1 to both sides, we have k, which is a constant gain, times some complex expression, g of z, complex meaning complex number expression. If that's the case, well, then we could write this minus 1 in polar form and say, oh, that's the same as having a magnitude of 1 and an angle of minus 180 degrees. We are now wanting to sketch, as k is adjusted, the values that satisfy this expression. We want k g of z to equal 1 at an angle of minus 180. And for starters, let's just focus on the k's that are non-negative. You can examine negative values of k, but that's just adding one more wrinkle. And to learn this, to learn the rules, we are focusing on non-negative values of k. So let's just say if k is non-negative, then the phase of the angle of kg of z is the same as the angle of g of z. If this is non-negative, it's not changing the sign, it's not changing the angle of whatever this complex number has for an angle. We now want to know, when is the angle of g going to equal minus 180, and that then says that for all values of z that satisfy this equation, their angles, when plugged into the appropriate g of z, whatever our plant is, if those angles all sum up to minus 180, then those values of z in the complex z-plane will live on the root locus. So let's now see if we can sketch the root locus for this plant, 1 over z times z minus 3 halves, and find for different values of k from 0 up to infinity what points in the z-plane belong on the root locus, or in fact are possible closed loop pole locations. And it could be that all of our possible closed loop poles are unstable. We want to know, is it possible for any of those to simultaneously produce a stable closed loop behavior? Well, initially for k equal to 0, we had a pole at 3 halves and we had another pole at the origin. Let's now, well, the last example, all of our closed loop poles for a proportional controller stayed on the real axis. Is that always going to be the case? Well, let's just see. And now we want to ask the following question. Which points, the star, the box, and the cloud, lie on the root locus? Do they all three? Is our root locus for this particular plant going to be passing through all three of those shapes? That's what we're asking. Our plant was this g of z equaling 1 over z times the factor z minus 3 halves. What's the angle of g at star? So now we want to know, at this location, what's the angle contributed by each of these poles and zeros, if we had zeros there, that we would have to move through or look to get to star? Well, the angle of g of z is going to be the sum of the angles of our numerator. We would look at what's up here. In this case, it's just a constant, so we're really saying what's the angle of 1, and that's 0 degrees. That 1 could be written as 1 at 0 degrees, and we're saying what's the angle of that? Well, that's now just 0 degrees. So a lot of times when you see a positive constant in the numerator, we just associate that with no angle. It's 0 angle, but a lot of times we don't even indicate it as an angle. So we have no finite zeros to produce any angles to get us to this point. What about the poles? Well, now we're subtracting their angles, because really, if you look at this, this is 1 at an angle of 0. This is now the angle of z, and it's also the angle of z minus 3 halves. If z is a complex number, that could be written as r e to the j theta. This is also a complex number for some choice of z, so this is an r1 e to the j theta 1. And this is e to the j 0 degrees. How do we find the effective angle? Well, here we just combine the exponents. We have the angle of the 0, which is 0, and then we subtract all of these angles in the denominator, which we had theta and we had theta 1. That's what we're doing now, to find the overall angle of g of z. That's what I'm going through, or saying now, in this expression. the sum of the zero angles minus the sum of the pole angles. What's the angle that this pole at 3/2 has to look through to get to that star? Well, now the angle is, if the star was up here, do you see that the angle would be right there? If the star was here, then that pole would have to look through that angle. Well, in this particular case, it looks through what angle? Well, it looks through an angle of 0 degrees. What about the angle that this pole looks through to get to that star location? Again, it doesn't have to move in an angle relative to the angle that the pole at 3/2 looked through. So what are these angles? These angles, now we could say this is 0 degrees, but it's nothing. Minus 0 plus 0, this is 0 degrees. In order for star to be on the root locus, remember, we needed the angle to be minus 180. And we've just computed that the angle at star is 0, so this star is not on the root locus. What about the box? Now the box, what angle does the pole at 3/2 need to look through? Well, now the angle is measured relative to the positive line segment moving in the real direction. So now it has to look all the way around, and that angle is now 180 degrees. The angle again is measured relative to the line segment, positive real line segment going to, well, positive says it's going to the right from that pole or 0. What's the angle that x has to look through? X again is looking through 0 degrees. So in this case, the phase of g of z at the box, the zeros, there are no zeros, but we subtract an angle of 180 degrees and an angle of 0 degrees due to the pole at the origin. This now is minus 180 degrees. So in fact, this point is or belongs on the root locus. So now we know that this segment must belong on the root locus, and anything here, we could have put that box anywhere, and the angle that the pole at 3/2 would have had to look through is 180. The angle the pole at the origin looks through is 0. So any point from 0 to 3/2 has an angle of minus 180 degrees. All of those points then belong on the root locus. What about this last location, the cloud? Again, we have no zeros to contend with. And what do we have now? If these poles are looking over to the cloud, this one has to look through 180 degrees. This one has to look through 180 degrees. So now this is minus 180 degrees plus another 180 degrees. This now says, oh, that's minus 360 degrees, which you could also say is equal to 0. That likewise is not on the root locus. We've now separated this real line segment into 3 different segments. We have one segment here, we have one segment here, and we have one segment going all the way to minus infinity. This segment goes all the way to plus infinity. I talk about this in other classes saying assume this real line looks like a loaf of French bread. We've now cut that French bread into 3 pieces or segments. We have this segment, and that segment. And there's only one segment corresponding to allowing the root locus, the closed loop poles that satisfy that closed loop denominator expression, to be roots of our closed loop characteristic equation. And those are now indicated by the red line segment. As we will learn in subsequent rules of our root locus, is that this pole goes to the left, this pole goes to the right. They can't just stay stationary as you adjust the gain k. Here was k equal to 0, k equal to 0. We increase the gain at some point, and in this case, since we just have 2 poles, let me get rid of some of this extra drawing. We just have 2 poles. They will now meet halfway between themselves, or 3 halves, 1 1/2, split in half, 3/4. At 3/4, one will go up, one will go down, and this is now the root locus diagram. This pole goes off to infinity. This pole, as we crank up the gain, goes off to infinity in the negative direction. Those are now approaching zeros at infinity as we adjust the gain k. And so now as k goes to infinity, we're moving there, and we're moving there as k goes to infinity. We started at 0, and as we crank up the gain k, the root locus branches, and we have 2 branches. We have this branch, let's say, and this branch. We don't know which one goes up and which one goes down. I just arbitrarily selected those. But we now have 2 branches on our root locus, and one goes to a 0 at infinity and the other goes to a 0 at infinity. This is now our root locus diagram for that system, which originally started unstable, but you can see that there is or are values of gain k that will allow both branches to simultaneously live inside the unit circle simultaneously. And until we crank up the gain to get us to this particular value, we will stay stable. So up until we get to, and now I've run out of symbols, but let's just say that there is the gain k to get us stable. Then once we hit the unit circle positively or negatively, that's the last, or that's the maximum gain to stabilize this system. We're now going to look at how do we design controllers based on these root locus shapes. We need to learn how to draw those shapes, but once we do, now we can see that as long as k is allowed to be bigger than k at the tall rectangle and less than the k at the triangle, we will have a stable system. That's where we want to go.